All right, today we're diving into this really fascinating world called Computational Fluid Dynamics, or CFD for short. It's this incredibly powerful science that lets us predict and actually see how invisible forces like air and water flow and interact with, well, everything around us. We're talking everything from a Formula One car to a giant skyscraper. So it really all kicks off with this huge challenge. How does an engineer design a race car to just slice through the air with minimum resistance? Or how does an architect make sure a new skyscraper can stand up to hurricane force winds? I mean, they're literally battling forces they can't see. And, getting it wrong, that's just not an option. This is exactly where CFD comes in. So here's the game plan for how we're going to break this all down. We're going to start with the problem itself, this invisible world of flow. Then we'll look at the practically unsolvable equations that describe it. After that comes the brilliant, pixelated idea that makes CFD possible in the first place. We'll touch on how computers do the heavy lifting, how we deal with pure chaos, and finally, we'll see how all of this technology is shaping our world every single day. Okay, first up, this invisible world of flow. Fluid dynamics is, at its heart, the study of liquids and gases in motion. And you see it everywhere, from the simple swirl of cream in your morning coffee to the complex rush of air over an airplane's wing. All these movements, believe it or not, are governed by these deep physical laws, and understanding them is absolutely crucial for designing just about everything. Okay, so here's where it gets really interesting. The thing is, scientists have actually known the source code that describes how fluids move for almost 200 years now. The catch, the equations themselves, they're just mind-bendingly complex to solve. Yeah, they're called the Navier-Stokes equations, and on paper they perfectly describe how things like velocity, pressure, and density all dance together in a moving fluid. But here's the kicker. For pretty much any real-world situation, like air flowing over a car, you can't just solve them with a pen and paper. There's no clean, exact answer. That's because they're nonlinear, which is just a fancy way of saying a tiny little change can lead to these massive, totally unpredictable results. It makes them just notoriously difficult to crack. So, right, if you can't solve the whole problem at once, what do? Well, this is where we get to the big aha moment, the beautiful, elegant, pixelated solution that makes all of modern simulation even possible. The truly brilliant idea, and this really only became practical once we had powerful computers, is this. Instead of trying to solve the flow for the entire space all at once, you break the big impossible problem down. You chop it up into millions or even billions of tiny, simple little problems that a computer can actually handle one by one. This whole idea has a name. It's called discretization. Let me walk you through how it works. First, you define your space, say the air around an airplane wing. Second, you cover that whole space with a grid, or what's called a mesh, creating millions of tiny cells. You can literally think of it like the pixels in a digital photo. Each one is simple. Third, the computer applies a simplified version of those physics equations to every single cell, solving for pressure, velocity, you name it. And then the magic happens. The computer stitches all those millions of tiny, simple solutions together to create this stunning, high-resolution picture of the entire flow. Okay, so let's dig a little deeper. How does the computer actually, do the math inside each of those little digital cells? Well, the most common way to do it is called the finite volume method. And what's so cool about this is it really taps into the physical intuition of what's happening. For every single one of those tiny cells in the mesh, the computer ensures that whatever flows in must also flow out. It's basically like a super strict accountant for physics. It does a perfect budget balance for mass, momentum, and energy, making sure the laws of physics are never, ever broken, not even in one tiny little volume. And this quote right here, it just nails why engineers have so much faith in this method. See, the math the computer is doing isn't just some abstract thing. It's tied directly, one-to-one, with the real-world laws of conservation that govern everything. That direct connection is what makes it so incredibly powerful and reliable. Okay, but wait, there's another huge wrinkle in all of this. Turbulence. That chaotic, swirling, totally unpredictable behavior you see in smoke or a raging river. Trying to simulate every single tiny eddy and swirl in that chaos, it would take more computing power than we have on the entire planet. So yeah, we need another clever shortcut. And that's where something called turbulence modeling comes into play. The idea is, instead of trying to calculate every single tiny chaotic swirl, which is basically impossible, we use these really smart, well-tested models to just approximate their average effect on the bigger picture. It's a brilliant and absolutely necessary compromise that lets us get practical answers in a reasonable amount of time. So what you have is this really critical trade-off. On one side, you've got what's called direct numerical simulation, or DNS. It's the gold standard. It simulates everything, down to the tiniest detail. But it is so computationally expensive, it's just not practical for most things. And then on the other side, you've got turbulence modeling, which is what makes it possible to actually design a new car or an airplane on a realistic timeline and budget. For the world of engineering, it's the absolute workhorse. All right, so let's bring this all back to the real world. After all this talk about equations and pixels and models, where does this stuff actually impact you and me? And the answer is, well, pretty much everywhere. It's in the sleek aerodynamic design that makes your car more fuel efficient. It's the engine behind the weather models that predict hurricanes. It helps design the incredibly complex jet engines that fly us around the globe. It's even used to design life-saving medical devices like artificial heart valves. The big takeaway here is that engineers can now test hundreds, even thousands, of different designs on a computer, which massively speeds up innovation and cuts down on the need for expensive physical models. So, when you boil it all down, CFD is basically our digital wind tunnel. It's like a virtual lab that gives us a kind of superpower, the ability to see the invisible, to make sense of the complex, and ultimately to engineer a better, safer, and more efficient world by truly mastering these powerful forces of flow. I mean, it is a genuine revolution in engineering and science. And that leaves us with this really exciting question to think about. As our computers get even more powerful and our digital worlds become more and more real, what's next? What amazing problems are we going to be able to simulate and solve tomorrow?